So last Thursday we talked about a little bit of the 2D interpolation, right? I just want to give you a flavor of this through, let's say, tensor product. I didn't quite finish it, but let's do a simplest case, so at least you have some very basic idea on what to do. All right. So if we have, again, as I was saying, what we do is that we have a function along the x direction, and then a function along the y direction, and you write you are using, so you have a function which is supposed to be a bivariate function. It's a function of x and y, right? We approximate it by a summation, all right, of, let's say, I is from 1 to something, to some number n, all right? You're going to have a function of x, g I x times h I y. That's called tensor, right? Tensor product. Let me show you, right? Let me show you. For the simplest case, we can use what we did in 1D to create something, for the 2D, right? So if we have a rectangle, a small rectangle, let's say, right, from x0 to x1 and y0 to y1. Now it's 2D, right? It's 2D. In general, if you have, say, you want to have a larger domain, what you do, one way you can do is that if I can subdivide this into many smaller triangles. It's like what we do in 1D, right? You cut the interval into a bunch of points. So we talk about, in 1D, we talk about x0, x1, x2, all the way to xn. It could be n plus 1 points on the line segment, right? So here we do that as well, and if we focus on 1 liter square, right? This is that. Okay, this is that. So here, of course, we're going to have x0, x1 to x, I don't know, 2, 3, 4, 5, 2, 3, 4, 5, 6, right? And here you have y0, y1, y2, y3, y4. So that guy would be x2 to x3, and then y2 to y3, right? Okay. Suppose you have a function on this larger rectangle you want to approximate. Okay? And you take out any such small rectangle, right? On this small rectangle, what do we do is we can, if we focus on the x direction, we can define. We want to have 2 points, right? We can define the as we did in 1D, the characteristic polynomial. All right, polynomials. Okay, so we're going to have a guy L2x, and then we're going to have L3x, right? The notation doesn't really matter. I can call it anything. The two function. Recall we in 1D, right? What do we have? Given x0, x1, xn, right? We can define the Li of x. A degree n guy is what? The x is a product x minus xj, right? Divided by xi minus xj, right? We did this for the degree 2, and here j runs through all the indices, but j is not equal to I, right? You say j is not equal to I. That was the characteristic polynomial. So here we have 2 points. 2 points. X minus, that guy is not himself, right? So we're going to have x minus x3 divided by x2 minus x3, right? And L3x is x minus x2 divided by x3 minus x2. So you're going to have a function, 2 points, a linear function along the x direction is equal to 1 at x2 and 0 at x3. That guy is 1 at x3, 0 at x2. Right? So that's the x direction. And the y direction, so that's just a side note. The y direction where y2 to y3, right? The characteristic polynomials are, because we use L already, we're going to use m2y is equal to, again, this guy should be 1 at y2 and 0 at y3, right? We're only focused on the y direction. You do it direction by direction. That's the idea of the tensor. So it's y minus y3 divided by y2 minus y3. And your m3y is what? Y minus y2, right? Divided by y3 minus y2. Okay. So you are using a degree 1 along each direction. And the interpolant on this piece is then written by, you're going to have the tensor product of all these functions. This with that, and this guy with those two. So if you look at that and if I define a function, right? If I define a function, let's say we have f of xy, right? We have f of xy, some function, some non-polynomial function. Remember, we were talking about approximating function by polynomials, right? Now here's 2D. You have 2D function. If we define this f1 xy, something to approximate it, right? To be, I have my f, all right? I evaluate at the x2, y2. I multiply that with my L2x, M2y, right? Plus, I'm going to have my x2, y3. I have L2x, M3y, plus my x3, y2, L3x, M2y, plus the final point, x3, y3, L3x, M3y. I'm multiplying each of those basis functions along the x direction with each one on the y direction. We get 2 times 2, right? 4 basis functions for 2D basis function. These guys are equal to 1, because for that to be 1 at this corner, it must be 1. They're both 1 times 1. At this corner, right? It's L2x and M3y at that corner. So we get 4 characteristic polynomials, for 2D characteristic polynomials for each corner, for the 4 corners. Those 4 guys is equal to 1 at that point and 0 at the other 3 points. You see that? So this is the same thing as 1D, right? For example, the L2x M2y, this is going to be 1 at x2 y2 and 0 at x2 y3 x3 y2 and x3 y3. The same thing is happening for the other 3 basis functions. So as a consequence, right? As a consequence, this interpolant, this approximated function f1, if you plug in xi, yj, this is actually equal to your original function f at xi, yj. I is equal to 2, 3, j is equal to 2, 3. Let me make sure you get. So yeah, this is called Q1. All right. So the QK, the QK would be a PK tensor product with a PK. Right. So in the Q1 case, this is for the 2D function. Then you're going to have your 1 and x with your 1 and y. Right. Which will give you 1 x y x times y. Those are the bases for your Q1 space. It's a space that has those functions. It gets a little bit trickier when we talk about space, but you could add a point, right? You could add a point there. Let's say, you could add a point there for each little rectangle. If I use 3 points along the x, and then 3 points along the y, what's the degree of the polynomial you can fit for each direction with 3 points? Yeah, P2, right? P2. A P2. So here, to be more rigorous, this is of a polynomial for xy. This is defined to be this along x, that's along y, right? So you can have a quadratic polynomial along x, right? It's quadratic along x. This multiply with this tensor by this notation. What we meant is that what we did above, right? This is along y. That means you have a few for the first set, a few for the second set, right? You have 2 for the one above. We have 2 for the first set, and 2 for the second set. You multiply by this funny multiplication. It's the tensor product, all right? You get 4 because you multiply each of the first set with each of the second set. So if it's degree 2, how many do you get? If it's degree 2 along each direction, degree 1 we already have 4, right? You have 2, so 1x and 1y. You get 1xy, xy. Or as we did above, you have L2, L3, M2, M3. You multiply, you get 4, right? So each of these is the first set. Each element in the first set should be multiplied with each element in the second set. That's 2 times 2 is 4. For degree 2, if you do a quadratic, you're going to get 3 characteristic polynomials along the x and 3 characteristic polynomials along y for a total of 9, right? 9. Yeah. each of the first would be met with each of the second, right? So you're going to get 3 by 3 basis functions, right? Functions. This is your Li x mj y, right? Or the possible ij's. You get 9 for this Q2 set of polynomials. That's Q1 means degree 1. Q2 means you take tensor product of the polynomial degree 2s. Polynomials with degree 2. You take a 1D polynomial of degree k, and you multiply them this way. All right, by taking all the possible combinations, you get a qk. Does it make sense? So if you write down, if we follow the monomials, we're going to have these, right? We're going to have 1 x y, right? X squared, x times y, y squared, right? And then we have x cubed, x square y, x y squared, y cubed. All right, and so over here we're going to get x squared, y squared, and we have x to the 4th, x cubed y, x y cubed, y to the 4th. I'm sure you have seen this in somewhere else. So these guys would make the Q1, right? And if they will do one more, those would make the Q2, right? Would make the Q2. So that's Q1, that's Q2. All right. Again, every is not normal multiplication. This means that everyone in the first set should be multiplied with everyone in the second set, right? That's what that's why the 1x x squared, 1x x squared, with this a funny multiplication, you get 9. All right, the next part. So that's part 3, right? We did the zeros, and then we did the interpolation. The first part is zeros, looking for zeros. The schemes to solve for the zeros of nonlinear function. The second part is the interpolation, right? The third part here is we'll devote some time to do the so-called numerical integration, right? Numerical integration. Numerical integration. So you're integrating a function f of x dx. All right, f of x dx. So what is this? You integrate. So you drive, right? You drive a car with speed that's constantly changing, right? You integrate your speed, you get what? The distance, right? The distance, how far you have been driving, and you integrate a factory output per day, right? A speed of the output, let's say, and also a speed. You get the total output along any period. So integration is everywhere, right? It's really everywhere. And the approximation of the integration is also everywhere, because we're not really, as you might know, right? When in real life we don't really integrate the way we do in calculus. That's a numerical integration. What you do a lot is actually doing things numerically, right? And for more higher level of simulations, we also need to do a lot of integrations. And if you know more tricks on how to do it accurately, your simulation will be better and faster. So we have a function, right? and a function f of x, and we need to integrate from a to b. We need to integrate from a to b. Okay. What's the meaning of this integral from a to b? In relation to this shaded area. It's area, right? It's area of the shaded area. And it's a signed area, right? It's a signed area. Which means if we have a function which is negative, right? Then it's not really the algebraic area, it's the difference of these two areas basically, right? From A to B. If the function sign is negative, then there is a negative area. Okay? So again, for this class, we talk about the numerical, right? The numerical value of this integral, right? Numerical value of the integral. So in calculus, for some of the functions, you can integrate by hand. That's not the case for many functions. In most cases, in real world, you cannot integrate by hand. We have to do it on computer. That's why this is useful. We're going to use ni, right? N for numerical, I for integration of f to denote this. This is to approximate ab f of x dx. Right, f of x dx. We're going to talk about a few choices to do that, right? So maybe we can start with that now, actually. To calculate this area, right? Any idea? Like this guy, right? You have from point A to B, okay, point A to B. Your goal is to calculate the area. So to always think about this geometric meaning, right? So maybe you can connect these two, and you would make a what? A trapezoid, right? The height might be different. Yeah. It's quadrilateral. Yes. And I mean that's slightly more complicated. Another way we can do this is as you, I'm sure you have seen from calculus. If we do the following, right? If we have this guy, I'm just plotting that again. Here. Let's make it. You can use this rectangle, the left end, right? The left end rule. I'm sure. How many of you have seen this in calculus? Some version of this, right? And of course, you can do the right end guy. You can use rectangles to approximate this area. And the idea is that if A and B are close enough, right? If the distance between A and B is small enough, which means if they are far away, what do? You split them into many pieces, right? You split them into many pieces. Then each piece can be approximated well by a rectangle or trapezoid, right? And we'll be talking about even more powerful ways to do the integration, which gets even more accurate. This is called the composite, which again we'll give more details soon, right? A composite rule. So the first one if you use 1 point, right? If you use 1 point, you don't have to use two endpoints. You can use something in the middle, right? What would be a better choice for if you use 1 point? That would be a little bit of the motivation for the midpoint rule. The midpoint rule, a very if you only use 1 point, right? A very intuitive motivation to use the midpoint is that if you have a straight line, a linear function you want to integrate, okay? For this case, if you use the left end or the right end, there is an error, right? You're computing. If you use the left, you're computing less than you should. If you use the right, you're computing more than you should. But in this case, if you use the middle, right? Then it's actually exact. You see that? The part that you missed is exactly compensated by the part you included. Right? So anyhow, that's a midpoint rule. And what we mean by that is that we're going to take the midpoint, right, f, evaluate at a plus b over 2. That's the midpoint, right? So that's the height. What should we multiply by to get the area? Yes, the base, which is b minus a, right? Just think of this as area, then you know what to do. And what we're doing is we're using a degree 0 function to approximate our f. So we're going to use that ni sub 0 of f to denote it, right? To denote it. We're going to introduce, as you read the book, you'll see a degree, the so-called degree of exactness. Degree of exactness, which is the maximum R such that the error, right? The error, which is En of f, okay, is exact in integral minus the numerical integral, right? If this error is 0, right, for f being a polynomial of degree r, right? Polynomial degree r. So you come up with approximate way to do your integration. If it's exact for polynomial degree r, the maximum such r is called the degree of exactness. The highest degree polynomial, the highest possible degree polynomial that you can integrate exactly. Okay. The higher the better if you want to improve your accuracy, right? So, I don't know if you were following. So here, the midpoint rule is this guy. What is this guy? This is at the midpoint, right? The x is a plus b over 2. The y is f evaluated at that point. Right? That's why we're having this formula, right? This formula. The height of this rectangle times the width. Is that clear? So for this way, right? For NIF, for the midpoint rule, for the midpoint rule, the degree of exactness is equal to what? Can it integrate degree 0, which is a horizontal line, exactly? Yes, because it's a constant. You take the midpoint, you get the same constant, right? As we just argued, you can integrate at degree 1, no matter what the slope is, because you're going to get exact cancellation, right? For the part you missed versus the part you included, which you should not have, right? They're the same. So it's exact for degree 1. All right. And we can actually prove it by looking at the arrow, right? By looking at the arrow. For that, we use our, the same old trick, the Taylor series. Okay. So what we do is that you should integrate this f. F can be any complicated function, right? Any function. And if I'm going to define this guy. I'm going to define the midpoint to be C, right? The A plus B over 2, that's equal to the C. It's equal to the C, right? And we can expand this guy. We can expand f of x around C, because that's the midpoint we're taking. Okay, so this f of C plus f prime, the derivative at C times x minus C, right? Plus f double prime at C over 2 times x minus C squared for some C on from A to B, right? From A to B. Okay. There exists such a C on the interval. We just don't know where it is for a given function. Okay. So what are we having? The first we are trying to integrate the function exactly here, right? And we see how far that is away from the numerical value that we use. And you see immediately where our numerical value is, which is the first term. We're integrating f of C. C is a constant. F of C is a constant. We're integrating f of C from A to B. That's fc times b minus a. That's exactly our numerical value, right? That's what we did above. F of C times b minus a. Plus the second term, f prime C times x minus C, right? You can either integrate it, or by looking at this, we are talking about what? We're talking about this function is equal to f prime C is a constant, right? This is what is it? This is f prime C times an integral from A to B of x minus C is a midpoint, which is a plus b over 2 dx. What do you get? You get 0, right? You get 0. Plus the second term is 0. Again, you can integrate that out, you'll see that's 0. Because this is like that's like calculating a line like this. Is 0 there? Okay. Of course, we still have the last one, which is f double prime C over 2, right? Over 2. Of the x minus C squared. The antiderivative is x minus C cubed over 3, right, from A to B. The second term is x minus c squared over 2 from A to B. You plug in A and B, you get the same guy. You subtract each other, get 0, right? Integration from calc 1. And for the last one, we have f double prime cos c over 2, right, over 2. We're going to get a b minus c, right, from A to B. What do we get? So you're going to get twice, right, of I still have that 1 over 3. You're going to have this b minus a over 2 cubed, right? The b minus c is b minus a over 2. B minus is b minus the midpoint, which is half of the length from A to B. Okay. So, this is FC times b minus a plus we have 2 cubed times 3, we'll get 24. 2 cancel with 24. Right? Oh no, you have another 2. You have another 2 below for the f double prime. So 2 cancel with that 2. So 24 left, right? So if I denote my difference between A and B by a capital H, we're going to have h cubed over 24 times f double prime cos c, right? Cos c. Okay, cos c. Which means the error for the midpoint rule is h cubed over 24 times f double prime and some cos c. Some cos c.
So
yeah.
It's
This error, right? This error, the error contains f double prime, right? As you see, which is 0, right? Which is 0 if f is linear, right? If f is linear, we're integrating f. The error is in terms of f double prime. If f is linear, then the double derivative is 0, so the error is 0. Which on the other hand again shows that if you are integrating a linear function, you're going to get exact integral. The error is 0. If f is quadratic, you're not going to get 0, right? You're not going to get 0. Yeah.
Why did you choose to use C for f double prime instead of f prime?
So let's talk about the composite rule. If we do this in the composite midpoint rule, that's the case when again you're going to take, if your A and B are relatively far away from each other, what you do is you take A, B, you subdivide them into many pieces, all right, and then you take the midpoint of each piece. You take the midpoint, all right, midpoint here, midpoint here, midpoint, all right. If I have, if my A is x0, my B is my xn, right? So we subdivide AB into n elements, right? N elements and line elements and smaller line segments. Maybe that's better instead of fusing. That's a more advanced language. N line segments. All right, and x0, x1, x2, xn. Those are the nodes, the points. N plus 1 points make n intervals, right? Line segments or just intervals, yeah. So number 2 is you apply the midpoint rule on each smaller interval, all right? Smaller interval, which is we're going to do a summation from I from 1 to n, right? We have our f at xi, that's the height, right? Here, if here is our xi, we're going to take this rectangle, right? So we're going to use the height times what? Is that b minus a as well? No, right? So is that b minus a, if you did that evenly, it's b minus a over n, right? If we define, we're going to call that little h, right? Little h. So it's a height times the little h. All right, multiplied with the corresponding guy. Does this make sense? You just take a whole bunch of intervals and do this on each interval, right? On each interval. The error, if you do this way, the error, right? The error is that you're making some error on each interval, as we just analyzed above. If we do it on one interval, that's the error we're making. It's 24, right? Is that the capital H, because we did analysis from A to B. Now it should be the little h, h cubed, right? H cubed is summation, and this with double prime, we have double prime of the c for that interval, c I, right? I is from 1 to n. You're committing an error everywhere. Committing one error for each interval. Okay? Yeah? All right. So this this is if we're going to treat as if all the c are the same. There's some calculus theory that allows us to do that. We're not getting into the details today. Then it looks like we're just factoring out the efficacy. Then you're going to get h cubed over 24, right? From 1 to n, right? And how many of those you're getting? You're getting n of them. They're all the same. N of them, right? N of them. But we know this is f double prime. Sorry, f double prime c, and then you're going to have h cubed over 24 times your n, right? Which is, we know n is a this is n. Will show the n is b minus a over h. So you cancel out one h. Is f double prime h squared over 24 times your b minus a. That will be the error for the composite midpoint rule.